We can see that when we restrict this power series and we stop it at a certain n value, we've created a new polynomial. And that polynomial is doing a better job of approximating the function below it, or the function that you're trying to approximate. So we want to define that a little bit. We don't really know what a Taylor series is yet. Here's a hint, you've just been playing with that, but don't worry about that so much. We just want to define what a Taylor polynomial is. So a Taylor polynomial has a center at A. So for example, the one we were just looking at in Desmos is centered at 0. So the 0 is the center of the interval that we are creating for that particular function and power series approximation of the function. So we can create an nth Taylor polynomial by basically having, well, let me just do it this way. You create a series built from the derivatives of the function that you're trying to approximate at the particular values, whatever your center is. So if your center is at 0 or your center is at 1 or whatever. So you take f of a plus f prime of a, so the first derivative times x minus a, plus f the second derivative divided by 2 factorial times x minus a squared, and you keep going like that and extending until you get to the nth term, which would be the nth derivative. Remember, when it's in parentheses, that's a derivative. So it's the nth derivative of a divided by n factorial times x minus a to the n. More compactly, we can say that the polynomial is equal to some coefficient group where the coefficients are written like this, right? The kth derivative divided by k factorial times x minus a to the k, right? So that polynomial, that's kind of what we're playing with on that previous Desmos example, except we're letting n get larger and larger. And as we do that, we see that the polynomial is doing a better and better job of approximating the curve. And there's a few things to keep in mind here. Some of these terms might end up disappearing. Let's say the nth derivative doesn't exist. It's 0. Well, it exists and it's 0. So if that derivative is 0, then that term will go away. So the nth term polynomial might disappear, in which case the degree of the polynomial would be less than n. That's why they say the degree of the polynomial is at most n, right? Because it can't be any more than that, obviously, because n is where you stop, and it could be less than that if some of the terms disappear, in particular the nth term. The nth degree Taylor polynomial is just the nth partial sum for the series. You don't know what the series is yet, but the Taylor series is a power series, a particular power series, right? They have a lot of applications. These power series, and the Taylor series is one we're going to be playing with in the next section. They have a lot of applications, particularly in differential equations. There's a lot of electromagnetic theory that's backed up by power series and Taylor series, as well as combinatoric and probabilistic theory that uses Taylor series and power series. And the Taylor series is just a special type of power series. We'll talk about it more. Now, when you build this polynomial, of course, you're going to be off. And we can see that in our particular graph. So let me go back real quick. And let me make this, it's a little bit easier to see it like 3. You can see that the curve and the polynomial are not exactly the same. There's an error between them, and we call that the remainder. The difference between the function, the real function we're trying to approximate, and the polynomial that we're using to approximate it, that creates something called the remainder, which is this part right here. So let me write that real quick. So that difference between the function that we're trying to approximate and that power series polynomial, which we're calling a Taylor polynomial, but suffice to say, that's a power series polynomial, that difference is the remainder. And we were seeing that as n increases, that difference becomes smaller, but it gets further away from the center of your, well, where you've centered your polynomial. The Taylor series provides good approximations to functions near a specific point, and we can see that. The farther we get away from that point, in our case, the point is over here at 0. So the farther I get away from 0, the worse my polynomial is at approximating that e to the x curve. The closer I am to 0, the better they are, because the blue curve and the yellow curve are right near each other. Of course, if I increase my k, I'm expanding the zone for which the blue and the yellow are very similar, but one way or another, they will eventually separate. And the difference in between because even right now, the blue and the yellow are not exactly the same. I know Desmos draws them on top of each other, but there is a difference, and that's what that remainder is. But of course, as n increases, that remainder should get, hypothetically speaking, smaller and smaller, especially if I'm close to where I've centered my curve, which in this case is at 0. X equals 0 is where the curve is centered. And that's all what the next particular page is telling us. Well, it's telling us a couple things, and this creates the remainder theorem, which is saying that a couple things. One, this is what we've been looking at in Desmos. If I increase my k, then my polynomial does a better and better job of approximating. So when you look at that graph on the paper, what it's doing is showing you k equals 1. Actually, it shows you k equals 0, which I didn't even bother showing. I guess I could let it go to 0, let you see. So it goes from k equals 0, which is a flat horizontal curve, terrible, and then k equals 1, k equals 2, k equals 3. It's showing 1, 2, and 3 all simultaneously, and you can see that the curve is getting better and better and better. So that's one thing. And the other thing is saying that the remainders, that those differences, how far away they are, increase as I get farther away from my center. So let me write that down. So the picture on the left is once again showing us just one more time that as n increases, n being the number of terms in your polynomial, right? The nth term polynomial, nth Taylor polynomial, it's a power series polynomial, is doing a better and better job of approximating f of x. So this graph, these are actually the remainders, how off each of these curves were. And in other words, it's the distance between the e to the x function and these different curves. And they're actually color coded. So there's the yellow one, there's the blue one, and so on. And that nth term Taylor polynomial, they're better at approximating when you're close to your center. In this case, it's centered at 0. And the farther you get away from that center, the worse these polynomials do at approximating that curve. Right? And you don't want to get far away from that center, right? That's basically what it's saying. That remainder, that error gets worse and worse as we get farther away from wherever the, wherever the center is. I apologize for that noise. And that's what this theorem is telling us, basically, right? It's allowing us to basically have a way to gather evidence on how accurate our Taylor series, our power series is for approximating the functions. And we'd be able to get as many decimal places of accuracy as we want. This is what computer programs do. So they say, hey, do you want 10 decimal places? Do you want 12? What do you want? I'll make you a Taylor series that will get you as many decimal places as you like, because that's as good as you're going to get. You can't actually have the real function value because that's impossible to find or by algebraic methods. So instead, I'm just going to get you a decimal approximation. So computers do this all the time. And that's what I just wrote. Last but not least, there's another theorem that we're not going to get into too much, but basically it says that the series will converge to the function f of x if the limit of your remainders is 0 as n goes to infinity. In other words, if I let the number of terms I'm going to include in my polynomial go to infinity, if the remainders will then go to 0, that means that the curve is, the polynomial is matching that curve all the way along. And there's no remainder.